Are you noticing this? The weather around us no longer plays by the usual rules, bringing freak heat waves, unseasonable hurricanes, and shifting climate cycles. This has become the new normal. People see the changes and feel them firsthand, yet there is barely any comprehensive analysis of what is happening in the media. We hear fragmented news reports, but nobody is connecting the dots to show the big picture. We used to know what to expect in a month or in 6 months. Now everything is changing faster than we can adapt. What will happen tomorrow? In 1 year or in 5 years? One thing is clear: the climate has become unpredictable. Today we are going to piece together everything we know, figure out what is hiding behind the official reports, and understand what we truly need to brace ourselves for. The disconnect between what people experience and what they are told has been around for a long time. Over the past few years, it has become way too obvious to ignore. People are seeing the changes with their own eyes. A winter that never showed up, a drought in places that never had them before, a massive downpour in the dead of summer, and instances like these are only piling up. Isolated observations do not just magically form a big picture on their own. To make that happen, you have to constantly track the data and understand how events in different corners of the globe are connected to one another. This is exactly the missing link in most public conversations about the climate. One of the most glaring signs of change is the shifting of the seasons. Scientists say that spring in the northern hemisphere is arriving earlier than it did a few decades ago, and fall just drags on and on. Plants and animals are the first to react to this, and their response is the most noticeable. Plants are blooming earlier than usual, birds are migrating at different times, and natural rhythms that took thousands of years to develop are completely out of whack. Different species adapt at different speeds, and this creates a massive disconnect. Bugs show up, but the flowers have not bloomed yet, or they are already gone. This happens slowly, year after year, almost imperceptibly to one observer. Individual oddities are visible right away, but the big picture can only be seen after many years of observation. The atmosphere, the ocean, and the land are constantly exchanging heat and moisture within a single system. The main part of this system is the ocean. It absorbs about 90% of the excess heat accumulated from the greenhouse effect. Without this buffer, the atmosphere would heat up much faster. But for the ocean itself, absorbing all this heat definitely comes at a cost. The accumulated heat changes the water itself, making it less dense, altering how it moves, and gradually returning this heat to the atmosphere through evaporation. The impact of this process is stretched out over time, showing up in our weather months and years after the heat was first stored. In the year 2023, ocean waters were the hottest on record. The record hit all the oceans at once and held steady for months on end, something that simply had never happened before. This was not just a sudden spike, but rather the result of a long period of accumulation. It all comes down to the physics of water, because heating 1 kilogram of water by 1 degree takes roughly 4 times more energy than heating the exact same amount of air. This works in reverse as well, meaning water releases its stored heat much more slowly than it absorbs it. The atmosphere can cool down in a few days, while the upper layer of the ocean holds on to heat for weeks and months. Scientists call the ocean the slow part of the climate system because it takes a long time to charge up and just as long to discharge, stretching the effects of a hot season far beyond its normal limits. A warm ocean releases heat, and the atmosphere above it feels this quickly, sometimes within a matter of hours. The warmer the surface water is, the more actively it evaporates, and more vapor means more energy being released during condensation in the atmosphere. Tropical storms get extra fuel right as they move. In the summer of 2023, the abnormally warm Atlantic supercharged hurricanes to massive strength, leading to longer storms, heavier rainfall, and greater destruction on land. A similar effect happens with heavy downpours over land, as an overheated ocean evaporates more moisture, and the wind carries it deep inland. The very same pattern applies on a continental scale, except there it dictates the entire picture for the season. The North Atlantic determines almost everything for Europe, like air humidity, wind direction and strength, mild winters and cool summers. Westerly winds blow over the warm water, pick up moisture and heat, and carry all of this to the European continent year-round. This is exactly why London or Paris are noticeably warmer in the winter than cities at those same latitudes in Asia or North America. The flip side of this relationship is that Europe is incredibly sensitive to any abnormal changes in the surface temperature of the Atlantic. The North Atlantic acts like a switch, and its position determines exactly how the European summer or winter will turn out. When its surface is abnormally warm, the atmosphere over Europe reacts differently, and the usual weather patterns start behaving in completely new ways. During the summer of 2023, this relationship was on full display. The surface temperature of the North Atlantic ended up being higher than ever before in recorded history, and scientists called the event completely unprecedented in both scale and speed. Based on preliminary data, it was as if the ocean went through several decades of expected warming all at once in just a single summer. This was a specific Atlantic event with a clear beginning, end, and set boundaries, rather than just a general long-term warming trend. There is no direct cause and effect relationship with El Niño in the Pacific Ocean, even though some scientists are discussing a possible indirect connection between these two processes. The phenomenon is known as a marine heat wave, where the sea surface temperature stays noticeably above normal for weeks on end. This specific anomaly created an unusual thermal background over the Atlantic, and it impacted that European summer that many remember as totally out of the ordinary. Scientists had to piece together exactly how the warm Atlantic affected the air over Europe. A few things are still up for debate. The warmer the ocean surface gets, the more moisture it releases into the air, and this shifts the cloud cover over nearby areas, which is backed up by observations from various stations during that time. Based on the available data, shifts in cloud cover could have affected how much sunlight reached the surface of the ocean and the nearby land. Fewer clouds mean more direct sunlight, and this could have provided extra heat to the air heading toward Europe. The warm Atlantic acted as a background amplifier that heated up the air over Western Europe, but it was not the only reason for the intense heat that summer. The marine heat wave alone does not explain the whole picture, but the situation would have looked very different without it. Once the atmosphere and the ocean started feeding off each other, Europe went through something that used to be considered a rare exception. Scorching seasons that previously only happened once every few decades suddenly started happening more frequently than ever before. The summer of 2023 was one of the hottest on record for the continent. A blocking high-pressure system stalled over Europe, acting like a lid on a sizzling skillet, trapping the hot air in place for weeks. The summer of 2024 offered no relief and also turned out to be abnormally hot by European standards. 2 record summers in a row made scientists seriously wonder if this kind of heat has become the new normal for the continent. Why Europe specifically? The continent is warming about twice as fast as the global average, and this is not a coincidence or a glitch in the data. One of the reasons has to do with how the atmosphere over the region has been behaving in recent years. Blocking high-pressure systems periodically settle over Europe, and in some years they stick around for a really long time, keeping out clouds and cool northern air for weeks. As long as the high-pressure system stays put, the ground underneath it dries out, and the air above it heats up even more. The drier the soil, the hotter the air above it, making the high-pressure system even more stable, and the whole process just feeds on itself. The Mediterranean is a whole different story. Hot, dry air blows in from Africa to the south, while the sea itself warms up and holds on to the heat. This is exactly where temperature records get shattered so often because of the mix of dry African air and an overheated sea. Scientists can actually calculate the odds of a specific heat wave happening without anthropogenic warming, and the answer is usually the same. Without human influence, these heat waves would be much weaker or practically impossible. As these factors pile up year after year, every new anomaly becomes a little more likely, making it harder and harder for experts to just brush off individual events as mere coincidences. The Mediterranean is in a particularly tough spot because it is already dry, and climate change is making those rainless stretches longer and the temperatures during them even higher. A warm ocean does not guarantee rain where it is actually needed, but it definitely cranks up the heat over the land. The soil and vegetation dry out faster, and that dry, overheated plant life turns into fuel for fires. The longer the drought lasts and the hotter the air gets, the higher the fire risk becomes, and the faster the flames spread across the fields and forests of the region. For the Mediterranean, this is already a growing pattern, rather than a single isolated event, as every hot summer leaves behind scorched land and depleted groundwater. Nature takes the next hit even worse than the one before it, and recovery takes more and more time. A separate factor hits exactly where most people live, which is in cities. Asphalt, concrete, and building roofs absorb the heat of the sun during the day and slowly release it back at night, which is why a city block cools down much slower than a field out in the country. Humidity adds to this problem. At high levels, sweating stops working properly, and the body does not have enough time to cool down even at night. The exact same temperature under these conditions is physically more dangerous than in a dry climate, especially for older adults. Heat in the city and heat in the country at the exact same temperature feel completely different to the human body. In the city, a person takes a double hit: the heat soaked up by surfaces during the day and the humid air that stops the body from cooling off. All of these things are connected, and to see that, you need to take a step back from isolated cases. The year 2024 was the hottest on record for the planet as a whole. The average annual temperature went 1.5 degrees above pre-industrial levels, the exact threshold that scientists have been calling critical for decades. This means that the entire climate system as a whole has stored way too much heat, and not just one specific region or season. At the exact same time, ocean water temperatures spiked right alongside the air temperatures. And this overlap of the two processes was no accident. The extreme heat over land, marine heat waves, and the reaction of the human body are all links in a single chain with a common source. The oceans are not directly connected to one another, but changes in one spot ripple out to another through the atmosphere and ocean currents. This is how energy gets redistributed all over the planet. And scientists call these remote links teleconnections between widely separated regions. Some models suggest that the warming of the North Atlantic might have shifted air currents and impacted the trade winds over the Pacific Ocean, which ultimately dictate whether an El Niño forms and just how intense it gets. For now, this remains just a hypothesis, not a proven fact. According to several models, the Atlantic anomaly could have been one of the driving factors that pushed the system toward a phenomenon the media dubbed a super El Niño, even though that category does not officially exist in science. This represents the next major link in the overall chain. El Niño is often explained simply as a warming of the Pacific Ocean, but that is a lot like calling a hurricane just wind. In reality, the entire system of winds and rainfall across the tropical ocean shifts all at once, not just the water temperature. Trade winds change their direction and strength, rain zones shift, and heat transfers between the ocean's surface and the atmosphere. The effects are felt way beyond the Pacific Ocean, bringing droughts to some regions, floods to others, and unusual heat or cold to places where they usually never happen. Over the last half-century, a few El Niño episodes stand out as especially powerful. Specifically, the years 1982 and 1983, 1997 and 1998, along with 2015 and 2016. Each one proved just how widely the consequences ripple across the planet. The first one came as a total surprise, as the tracking systems back then completely missed it, failing to record it in time, while the entire world felt the aftermath. The second episode was long considered the strongest one on record, and that was exactly when the term Super El Niño really caught on. By some metrics, the third episode came incredibly close to that record, or even beat it. El Niño does not act like a localized anomaly in the Pacific Ocean, but rather like a global switch, changing how air moves all over the planet at once. Observational data paints a very clear picture, showing that strong El Niño episodes and rising global temperatures go hand in hand year after year. The warm surface waters pump extra heat into the atmosphere, and it spreads all over the planet, driving up the average numbers. That is why years with a strong El Niño regularly end up being the hottest on record for the planet. When long-term warming from greenhouse gases coincides with the extra heat from El Niño, both factors push in the same direction at the same time. This double pressure worried meteorologists even before the events of 2023 unfolded in full force. The problem was not the warm phase of the Pacific Ocean itself, but what it was overlapping with at that moment. The global ocean was already severely overheated by that time, and the alignment of two independent heat sources is rare. Usually different climate factors cancel each other out, at least partially, but that time both were working in the same direction. The American Weather Service and meteorologists from international organizations warned about this exact combination of factors ahead of time. When heat from the Pacific Ocean is added on top of an already warm ocean, the total effect turns out to be stronger than if each factor were working separately. A situation where such a strong, warm phase would coincide with such an overheated global ocean had simply never happened before. The warm phase in the Pacific Ocean has a specific feature that is often overlooked, which is that it does not end abruptly and all at once. The consequences drag on for months after its intensity starts to drop, because the ocean and the atmosphere transfer accumulated heat to each other with a delay. When the data shows the anomaly weakening, the planet technically has not had time to cool down completely. Some of the heat has already escaped into the atmosphere, some is dispersed through currents, and the system keeps reacting to a push that is already weakening according to the numbers. By some estimates, the warm phase added a few tenths of a degree to the global temperature on top of the usual increase. The end of the warm phase does not mean that everything will go back to normal on its own anytime soon. Temperature records could keep being broken long after the anomaly in the Pacific Ocean shifts into the neutral or even cold phase of its cycle. This shows up not just on thermometers, but also in the lives of fishermen, farmers, and energy workers all over the world. Warm water does not hold dissolved oxygen as well, which is basic chemistry that has been known for a long time. But the fallout for marine life has turned out to be worse than expected. When the oxygen concentration in surface waters drops, the usual habitat becomes unlivable for fish. They move to colder areas rich in oxygen. And this is happening at the same time in many parts of the planet, rather than just in one place. Areas that fed entire regions for generations are bringing in smaller catches year after year. This is a direct hit to the people and economies of places where fish has always been a staple on the dinner table. And food prices there are noticeably shooting up as a result. At the same time, the energy landscape is shifting, and for the exact same reason, the delayed effect of accumulated heat. During extreme heat, the demand for electricity to run air conditioning goes through the roof, and power grids are caught completely off guard, especially in areas where these kinds of heat waves used to be rare. On top of that, actually generating power is getting harder. Droughts are draining reservoirs dry, and hydroelectric dams are losing their output right in the middle of peak demand. Wind patterns are shifting too, and wind farms are starting to produce less energy at the exact moment people need it the most. The exact same phenomenon is driving up the demand for power while simultaneously cutting down our ability to generate it in different parts of the world. This is not just a one-time glitch, but part of a growing pattern that is unfolding right now and happening more and more often with each passing year. What used to happen just once a decade is now happening almost every single year, and each time it is no longer a surprise, but just the next event in an ongoing chain. Heat waves are dragging on for weeks, leaving absolutely no time to recover in between. The focus is shifting. It is no longer about how to survive something out of the ordinary, but rather how to live when this has become business as usual for entire regions. For a long time, each anomaly seemed to exist in a vacuum, completely separate from the rest. A heat wave in one region, a drought in another, a bizarre rainy season in a third. And at first glance, none of these events were directly connected to the rest. climate studies over the past few years have brought these isolated incidents together and revealed the link between them. Researchers did not call these events identical, but they did group them into a single system, and this completely changed the conversation about what is happening in both science and the media. The difference between understanding and ignorance is not about accurately predicting tomorrow or stopping a heat wave in its tracks. It is about seeing the big picture of the process, rather than just a bunch of random coincidences, and to stop acting surprised by every new event. In practice, this means cities have to be able to handle the kind of heat that used to be considered rare, relying on building cooling, power grid backups, and solid water reserves. Coastal and fishing communities need to plan for shifting fishing grounds well in advance, rather than just reacting after the losses have already piled up. Farming in dry areas like the Mediterranean needs a total overhaul, keeping in mind longer droughts and more frequent wildfires for years to come. We need to prepare not just for one anomaly, but for them to happen more often and with greater intensity, because the accumulated heat does not just disappear when the season ends. Understanding the mechanics of what is happening does not wipe out the consequences, but it does give us the chance to act proactively instead of just playing catch-up after the fact.